Hello everyone. Welcome back to the Heterogeneous Parallel Programming class. This is lecture 1.4, Introduction to CUDA, and we're going to be talking about data parallelism and threads. The objective of this lecture is to help you to learn about data parallelism and the basic features of CUDA-C, which is a heterogeneous parallel programming interface that enables the exploitation of data parallelism by using both CPUs and GPUs. And the topics that we're going to cover today are the hierarchical thread organization, the main interfaces for launching parallel execution, and the thread index to data index mapping. The phenomenon of data parallelism is that different parts of the data can actually be processed independently of each other. A very simple example is vector addition. When we add two vectors together, the elements can be added together independently. A0 and B0 can be added into C to form C0, and A1 and B1 can be added to form C1 independently of each other. So if we have a large number of elements in each vector, and we have a large amount of hardware, we should be able to perform all these additions in parallel. And that's how we can fundamentally achieve high performance in a CUDA program. So that's the reason why we're going to be using this very simple example to illustrate the basic concepts of CUDA. The parallel execution model of CUDA and its close relative OpenCL are both based on a host plus device kind of arrangement. So the basic concept is that when we start executing a piece of code or application, the application will be executing on the host. And host is typically a CPU core. And when we start to execute into a parallel part of the application, that's when we start to have an opportunity to use throughput-oriented device. So this is done by writing some specialized functions called kernel functions. These kernel functions are very similar to functions in the C programming language. They also take parameters or arguments. So that's why I showed that for a kernel function called kernel A, it will take arguments just like the C functions. However, they also take configuration parameters. And these configuration parameters are specially noted by 3 less signs in the front and 3 greater than signs in the back. In between, it gives a configuration parameter of number of thread blocks in the grid and number of threads in a thread block. So in this example on the right-hand side, we show that the kernel will be executed by a number of thread blocks, which are shown as rectangular blocks each with several threads in them. And then within each thread block, we will have a number of threads all executing in parallel. So then after the execution of the kernel function, we will return to a sequential execution, sequential part of the application. So we return to the host for sequential execution. And then when we reach another part of the application where we have an opportunity, we write another kernel B that can be executed in parallel. So the execution will go between host and device. Device in CUDA means parallel execution device. And most of the time, the device correspond to throughput-oriented GPUs. This picture shows the levels of abstraction in a computer system. When we typically when we have an application, the application solves a problem at the human level. So we will have natural language description of the problems that the application should solve. And then based on the description of the problem, we will define algorithms which have very well-defined steps of computation and a well-defined criteria for terminating the computation. And then the algorithms will be implemented with programming languages. such as C and C++ and so on. CUDA is really a programming language at the C level, and it's actually designed as an extension to the C language. And more recently, more and more of the C++ features are also available in CUDA. So CUDA is becoming more and more of a C++ programming language extension. However, in order to fully understand the behavior of the CUDA programs, oftentimes we have to go a little bit lower into the abstraction layers and look at the instruction set architecture and microarchitecture, which is the organization of hardware to be able to execute programs. And so therefore, we're going to actually go down a little bit in today's lecture just so that you can have a solid understanding of the execution model of CUDA. And this is based on a picture from Pat and Patel, an introduction to computing systems from bits to bytes and to gates and beyond. Let's go a little bit into the concept of ISA, or instruction set architecture. An instruction set architecture is a contract between hardware and software. Mostly, the instruction set architecture specifies a set of instructions that the hardware can execute. As long as the software consists of these instructions, the hardware knows what to do according for the software. So whenever we write a piece of code in CUDA, it will eventually be compiled down to the instruction set architecture level. And the program is the program is said to be at the instruction set level whenever it's compiled down to these instructions. So at this level, a program is really a set of instructions stored in memory that can be read, interpreted, and executed by the hardware. The program instructions will then operate on the data that are stored in memory or provided by input-output devices. The next slide shows a very simplified diagram of how the hardware is typically organized to execute programs that are represented at the instruction set architecture level. And this diagram is really based on von Neumann processor model, which is proposed by John von Neumann in the 1940s. Today, virtually all the processor cores are designed based on this, are variations of this particular model. So let's start with the bottom. The bottom here shows the control unit. And the control unit contains a program counter and instruction register. The program counter essentially specifies the location in memory where the hardware can find the next instruction that should be executed for the application. So there's a dashed line going from the control unit to the memory. Essentially, that is the data, the communication path for the control unit to deliver the PC value to the memory and demand the memory to return the instruction bits. And once the instruction bits return from the memory, it will be placed into instruction register, or IR. That's where the hardware will examine all the instruction bits and determine all the activities that need to happen in order to execute that instruction. And these activities are actually coordinated by the control signals, which are represented with by the dashed line going from control unit to the processing unit in the middle of the picture. These control signals essentially define the activities that the ALU, the register file, and other components in the processing unit need to take in every clock cycle in order to execute the instruction. And during the execution, some of the instructions will need to be able to access data, read or write data from or to memory. And that's indicated by the upward arrow and the downward arrow of the between the processing unit and the memory. So depending on the type of instruction, the execution will have activities in ALUs and register files and accessing memory and so on. Finally, some of the data will be moved back and forth between the memory and the I/O. The I/O represents the network and the disks and so on, and the displays and so on. So the data will be moved back and forth between memory and I/O. And so we're actually going to see a little bit of I/O activity as well for the rest of the class. So now we are ready to talk about more specifics about a CUDA thread. A CUDA thread is really a virtualized or abstracted von Neumann processor. You can think about every CUDA thread as one of these processors. So each of these processors will be able to execute a program. So the kernel function that we described is that program. And the hardware will actually generate a large number of these von Neumann processors, and each of them will hardware provides a large number of these von Neumann processors, and each of these processors will be executing that function, the kernel function. So, but it's virtualized in the sense that if you look at the hardware, the number of real processors may be much, much smaller than the threads that a CUDA program will create. So a lot of these threads will actually need to be executed by the real processors in turn. So some of them will be actively executing, and some of them will not be actively executing. And this is what we call context switching, and that will be we will elaborate on that very soon in one of the future lectures. So let's go into the way a CUDA programmer think about threads. So whenever a CUDA kernel is executed, it's executed by a grid or array of threads. So here we show a one-dimensional thread block. And let's assume for the moment that the grid has only one thread block for the moment. So all the threads will actually run the same code as we described before, but every thread will have a different index value or thread index value that it will use to compute memory addresses and make control decisions. In this particular example, we show that there are 256 threads in the thread block, and each of them will have a unique thread index from 0 to 255. And there's a piece of code that in the kernel that I'm showing in the box underneath, and that box is first calculates a I variable based on the thread index. This I variable is actually private to every thread. That is, every processor, von Neumann processor that correspond to those threads will have a unique I variable. Thread ID, thread 0 will have its own I, thread 1 will have its own I, and so on. Thread 0 will calculate its I value as 0 in this case, because the thread index.x value for thread 0 is 0. So I will be 0 in this case for thread 0. Thread 2 will have I value 2, and so on. And thread 255 will have I value 255. So when we execute the statement CI equals AI plus BI, the I value for every thread will be different. So thread 0 will be adding A0 plus B0 and assign that to C0. And thread 255 will be adding A255 plus B255 and assign that to C255. Now that we understand how a single thread block works, we can now expand to multiple thread blocks. Here we show a grid of threads that are organized into n thread blocks. And each thread block still consists of 256 threads. So here, every thread not only have a thread index, but also a block index. The block index variable is called blockIdx.x. The thread index is called threadIdx.x. These are predefined CUDA variables that we can use in a kernel. And they actually are initialized by the hardware for each thread. So you don't need to initialize these variables because the system initializes these variables for every thread. Now, when we form the data index, now we need to factor in both the thread index and the block index. So in order to calculate I, now we take the block index and multiply that by the block dimension, in this case 256, and then we add it to the thread index. So the thread 0 in block 0 still has I value 0 because the block index value is 0 in this case. So, but if we look at thread block 1, now all the threads are going to be seeing thread block idx.x value 256. So thread 0 in block 1 will actually have an I value of 256 instead of 0. And then obviously the next thread block, thread 0 in thread block 2 will have I value of 512. So this is as a result, the I values of the first thread block will range from 0 to 255. And all the I values from thread block 1 will range from 256 to 511. As you can see, now all the threads form a uniform coverage of all the array elements. 0 to 255 in the first thread block, and then 256 onto 511 in the next thread block, and 512 to 67 in the next block. So this kind of coverage is what we call the linear coverage of a one-dimensional array. By using this formula, we can make sure that every element of A, B, and C is covered by one of the threads. In reality, we may have each thread to cover more than one element, and we will come back to this point, but at a later point. But at this point, it's sufficient to understand just how we can map every thread to a unique array index, array element. So the threads within a thread block can actually cooperate through shared memory, atomic operations, and barrier synchronization. At this point, it's sufficient for you to just be familiar with these three terms, because we're going to actually go into much more detail. Essentially, shared memory allows the threads to exchange data. The atomic operations allow the threads to be able to coordinate their updates to the same variables. And the barrier synchronization allow the threads to force others to wait for them. So all these activities allow a coordination of activities across different threads. However, threads in different blocks do not interact. So thread 0 through 255 in thread block 0 cannot interact with the threads 0 to 256 in thread block 1. There's no real interaction that we can have between these thread blocks. So this is going to be important as we to understand scalability in your CUDA code. Now, the thread index and block index are not just one-dimensional indices. In CUDA, each thread block index can be a 1D, 2D, or 3D variable. So each thread index can also be a 1D, 2D, and 3D. That's why in the previous slide, we go back to the previous slide here, when we talk about thread index, I actually have block idx.x because we're only using the first dimension of the block index variable. in reality, many applications operate on two-dimensional data, such as images, three-dimensional data, such as volume in a differential equation solver for computational fluid dynamics. So that's why it's very convenient to be able to use 1D, 2D, or 3D block indices and thread indexes so that we can map that conveniently to a two-dimensional data or three-dimensional data and maintain and keep the program easy to read. So here I'm showing a two-dimensional block structure, and within each block, a three-dimensional thread structure. So when we look at the grid, we see that each block has two indices, the X and Y indices. And X is the first one, Y is the second one. And actually, it's the other way around. X is the right element, and Y is the left element. So at the top, we have block 0, 0 and block 0, 1. So Y equal to 0 for both blocks, and X equal to 0 and 1. And now the second row has Y value of 1, and X will vary from 0 to 1. Obviously, X and Y can vary from 0 to a fairly large number, usually in the tens or even in the hundreds. So now each dimension in CUDA can grow to 600 2 to the 16th. Now, when we look at each thread in a block, I'm showing a three-dimensional thread organization within the block. So I'm expanding out block 1, 1 here, and I show that in this toy example, there are 16 threads. Each thread has a unique three-dimensional ID. The X ID varies from 0 to 3, and the Y ID ranges from 0 to 1, and Z ID ranges from 0 to 1. And that gives us 16 possibilities. So as you can see, we can combine a two-dimensional grid organization with a three-dimensional block organization, or we can have three-dimension, two-dimensional, and plus two-dimensional. So this all depends on the needs of your application. As we mentioned, this kind of multi-dimensional index is very convenient when we need to do image processing or solve three-dimensional partial differential equations and so on. So this concludes the first episode of the Introduction to CUDA. If you'd like to learn more about the basic concepts of data parallelism and the basic execution model of CUDA, I would like to encourage you to read Chapter 3 of the textbook. Thank you.